First, let's add a markdown cell and some LaTeX notation. So I'm going to change this to markdown, put 2 pound symbols there. Right. Correlation. The LaTeX notation we're going to add is going to look like this. $2, and then we're going to have the Greek symbol for row, and then we're going to have an underscore, open curly brace, XY, closing curly brace, and then equals core, CORR, parentheses, X comma Y, closing parenthesis, and then $2. Let's see what this looks like. I think this makes a nice section heading. Just for completion, let's add 2 more pound symbols, $2, minus 1.0, and then let's have the following tag, /LEQ, and then we'll have /row, space, underscore, and then curly braces, XY, and then another LEQ tag. So /LEQ plus 1.0, and then $2 at the end for the closing tag. Now we've got the minimum and maximum values of the correlation in our heading as well. And in the LaTeX notation, the Greek symbol row is given like this, with the slash and then the keyword. We create the subscript XY with the underscore and then the curly braces. And finally, we've used the slash and then LEQ for the less than or equal to symbol. So now that we've added our section heading, let's calculate the correlation between the average number of rooms and the house price. Now, before we just punch in the Python code, what would you expect to see? Do you think this correlation should be positive or negative? Do you think that the correlation between the number of rooms and the property price is strong or weak? So looking at the LaTeX notation in our section heading here, pick out a number in your head between -1 and 1. Ready? Did you make your guess? Okay, so to get the answer, you simply call the core method on the series object. So data, square brackets, single quotes, price, dot, CORR, open parentheses, data, square brackets, single quotes, RM, will retrieve the price column from our data frame. So this is our series object, and then call the core method on that series object, and then as an argument between the parentheses for this method, we supply a single piece of information, namely the series that we want to calculate the correlation against. In this case, the average room size. Hitting Shift-Enter, we see that the correlation is indeed positive and around 0.7. And that makes sense, right? The larger the property is, the more rooms it has, the more expensive it should be. Now, as a challenge, I want you to do the same thing for the property prices and the pupil-teacher ratio. I want you to calculate the correlation between this feature and the property price. But before you type in the Python code, I want you to make another guess at the correlation. So pick a number between -1 and 1, and then write your Python code. Do you think that the house prices will be positively or negatively correlated with this feature? Now, figuring out the reason for this is probably harder than typing in the Python code. I'll give you a few seconds to pause the video and just give it a shot. All right, ready? Here's the solution. I can simply copy what I've written in the cell above, paste it in, and then change RM to the name of the feature that I want to calculate my correlation against. And this is PT ratio in all caps. And when I hit Shift-Enter, I see that the correlation here is -0.5. But why is that? What does this number actually mean? So the first one was a positive correlation. It was fairly strong, 0.7. And this is a fairly strong negative correlation, -0.5. Now, let's have a little think about why this might be. If you had one teacher and 2 students, what would the value of PT ratio be equal to? The PT ratio would be equal to 2 because there's 2 pupils and 1 teacher. Now, 2 students and 1 teacher is kind of like having private tuition. So if we take this thinking further, What if you had 15 students per teacher? Then the value inside PT ratio would be equal to 15. And with 15 students instead of 2, each student is getting less attention from the teacher. So what if that class size grows? What if you have 30 students? Then each student is getting even less attention from the teacher. And you can imagine the students in the back of the class giggling, passing notes, playing Clash Royale on their cell phones, and throwing paper airplanes, right? In other words, this PT ratio feature measures the quality of the education, the quality of the schools. The schools with many kids and few teachers are under-resourced, and they tend to have a lower quality of education. And this quality of education is reflected in the house price. If the PT ratio goes up, which is a bad thing because you have so many pupils per class, then the property prices tend to go down. And this is why we see a negative correlation. Okay, so we've picked out 2 correlations, one by one, against our target, against our house price. What if we wanted to calculate all the correlations at the same time? Because doing this one by one is going to be pretty painful, right? Well, Pandas has got us covered. In this next cell here, I'm going to take my whole data frame, data, and call the correlation method on it. So data.core parentheses and shift enter will produce this. This is an entire table that doesn't just show the correlations with the house prices. Those are in the last column here. It also shows the correlations amongst all the different features. For example, how the average number of rooms is correlated with the amount of crime. So in this table, you can still find these 2 values. So price versus room size and price versus PT ratio. If I go down here, the first value, 0.7, is here, and that second value, minus 0.5, is right here. But the other interesting thing about this table is this diagonal here. You see these cells of 1s? Along the diagonal, all the correlations are equal to 1. And that's because the correlation of a variable with itself will always be equal to 1. So crime correlated with crime is equal to 1. The correlation of number of rooms versus number of rooms is equal to 1. The correlation of age against itself is equal to 1, and so on. So you can pretty much ignore this diagonal. It's not telling us anything interesting. In fact, you pretty much can also ignore half of this entire table. You see, this table is symmetric. This value here, crime versus zoning, is the same as zoning versus crime. And industry versus zoning is the same as zoning versus industry. In other words, the 2 halves of this table split along the diagonal are the same. Let's come back up here to this correlation method and hit Shift-Tab on our keyboard to bring up the quick documentation. If hitting the little plus sign expands this whole thing, and we can see something kind of interesting. Now, it turns out that we didn't supply any arguments to this correlation method. There's no value here. We didn't put any inputs between these 2 parentheses. And what this means is that we're kind of going with the correlation method's defaults. And it turns out that there are multiple ways you can calculate a correlation. And we're using the default way of doing this calculation. Our specific type of correlation is the Pearson correlation. There's 2 other ones down here which we could have picked, but Pearson is the default correlation that we're going to be looking at. So I'm going to add this as a comment here in this cell. I'm going to say Pearson correlation coefficients. That way there's no ambiguity here. Now, since we brought up this table here, this kind of brings me to our next point. We spoke about kind of 2 things that we look for with these correlation calculations. We look for the strength and we look for the direction of the correlations. But there's actually also a third thing that we kind of care about, because in this table, we didn't just have the correlations between our features and our target, the house prices. We also had the correlations of the features with each other. So let me ask you a question. If two features were perfectly correlated, would that be a good thing? Or would that be a bad thing for our regression model? And the answer is, it depends. But it could be a bad thing and something that we probably want to discover early on. Let me explain the problem that high correlations between features could pose for our regression model with an example. Suppose you're a medical researcher and you're analyzing the bone densities of people. Your goal is trying to figure out what makes people have strong, healthy bones. And you have all this data on people, and you're running your regression. And the kind of data that you're feeding into your regression model includes a person's age, a person's body fat, and a person's weight. These are your explanatory variables. Now here's the catch. It turns out no one looks like this. The people who actually do look like this get put up on a stage and cast in movies like Conan the Barbarian. And the thing about these people is that they have a very high weight, but very, very low body fat. But in this world, there are very, very few tall, heavy, but lean bodybuilders. For most of the population, body fat and weight are actually really highly correlated. Most people who weigh a lot tend to have high body fat, and most people who are very, very skinny tend to weigh very, very little. So given this pattern in the data, what does this imply for the medical research that you're doing? Because body fat and weight move together, you're going to have difficulty telling apart their effects. In other words, body fat and weight are highly correlated, and it becomes very difficult to see the individual contributions to bone density of either of these two explanatory variables. One of these features is redundant. And this problem that you've just encountered in your hypothetical medical research actually has a name. It's called multicollinearity. Now, multicollinearity is a word that only a statistician could love. But put simply, multicollinearity is when two or more predictors in a regression are highly related to one another. So for this example, it was body fat and weight, which are very highly related. Each of these do not provide unique and independent information to the regression. Now, the result of your regression having this problem of multicollinearity means that the estimates start becoming unreliable and your findings stop making sense. Put simply, the model starts getting confused. But the thing to remember is that high correlations don't automatically mean that you have this problem of multicollinearity. I wish it was that easy. However, what it does imply is that we should be looking at these correlations between our features. We should be investigating if our features are highly correlated. And if we find a high correlation between our features, we should investigate why that is. The high correlations can be an early warning sign that there is some sort of problem. High correlations between your features are kind of like a toothache that make you go to the dentist. The dentist will then investigate further to see what the actual problem is. So, having introduced this topic, we're going to keep this in mind for our regression analysis stage. This is when we're going to be revisiting this question of multicollinearity.